All right, welcome back. We're going to do section 3.4 in this lecture, which is talking all about slope. Now, some of you might be hearing slope and thinking of a horror movie like, knife coming at you or something like, slope. It's not that scary. It's far easier than what you might think. Slope simply means change. And specifically, we're talking about a rate of change from one point to another. That's all slope is talking about. The concept of slope is actually super easy. So we're going to take a look at an example. This is the same example that you have right here in your notes. It is drawn to scale this time for me. And just to give you a quick understanding of slope, based off the notes that you have on the top, you've probably heard this as well in the past. Slope is simply talking about the rise over run. And we represent the term slope with the letter M. So we're looking at rise over run. What does that mean? Well, it looks at the change of how we are vertically shifting in the y-axis over the change of the x-axis. So the rise and then the run. And that creates a fraction thus known to us as slope. So if we were to look at this particular problem, got my 2 points. I'm going to make them a little bit darker so they're easier to see. Again, you can follow along right here on your notes. My first point, if I were to look at this, is this point up here. I'm going to look at, that's -3, +4. So it's a -3, +4. And this point is a -1, +1. Those are my 2-point values. Now, if I were to count the spacing between them, I would count my y values first. So from here, I have 1, 2, 3, and then my values going to the point from where I'm at, 1, 2. What I would see is that I have a slope. I'm going to write it right here. That went down 3 units, okay? So down 3 over 2 units. And so I have a slope of -3, 2. Now, the problem with this is you can only really use that rise over run concept if you're working on a graph that is to scale. And you've got to make sure that those points are actually on the indicated point. They can't be fractional values, because if they're a fractional value, now you're starting to run into an estimation, and your estimation may be off. So what we need is a system to calculate slope a little bit more precisely. And as you're looking at these 2 points that we moved from our rise and run, what we're going to do is say that we have 2 points. We have an x and a y in each point. So this is point 1, x1, y1. And we have a point x2, y2, just for classification purposes. I'm going to just specify, so this is a -3, 4. And this is going to be my other point of -1, 1. Just to put my points together. Now, rise over run. Let's talk about that concept. So we talked about the change for the rise, the change in the y values. So a change in y over a change in x. I'm using a little delta symbol to show change. That's all it's simply saying. We express this mathematically so that our slope, using my 2-point values here, show the difference between my 2 y values over the difference between my 2 x values. So it's the difference between the vertical and the difference between the horizontal. So pretty easy in concept, right? Now, I often get a question of, well, how do I know which point is which? It doesn't matter. It really does not matter. You can always go left to right if that's how you want to do your preference. but it does not matter which point is which. But what does matter is that you keep your points together. So notice that my y2 and my x2 from this point are stacked together, and that my y1 and my x1 from this point are stacked together. So you have to keep your points together to be able to work this, but it does not matter on the order per se. So let's work this out. Let's actually do some math with this particular problem. So I have a I have a positive 4 minus 1, my values for y, and my 4 is here, so that means this value has to be that negative 3, minus a negative 1. Whenever you encounter a double negative, just put the parenthesis, get it written first. All right, let's work through it. 4 minus 1 is 3. Negative 3 minus a negative 1. Well, that's like negative 3 plus 1, because double negatives makes that positive. So it's negative 3 plus 1, which is a negative 2. There you are. Now you might be saying, well, wait a minute, the negative was on top here, the negative is on bottom here. It doesn't matter, because if I have a negative, I can have it in front of a fraction, I can have it in the numerator of a fraction, or I can have it in the denominator of a fraction. Any of these three situations allows the negative to float up or down or out to the side, and that is perfectly fine. These are all exactly the same. You cannot have a negative in both numerator and denominator and mean this. It's not the same, because this is essentially going back to double negatives. Okay, so that being said, the rise over run in this situation worked out nicely because you have a graph to scale and the points are very, very clear as far as where they are. But mathematically, you can work this out precisely. And if you struggle with seeing the graph, or if you have any kind of issues there as far as trying to count, you can eliminate all of that hassle by just doing this mathematically. So I strongly suggest getting used to the mathematical performance here. Now, let's say that we have 2 points. I'm going to keep my slope formula, but I am going to write it a little bit higher up here, just so that it is out of the way. I'm going to put my squiggly line there showing I'm on a different problem. I'll box that so I don't erase it. So this is your slope. Keep that in mind. Very, very important. Okay, so my next problem just gives me points. It gives me 8, 3, and 8, negative 2. And it says, find the slope of a line passing through these 2 points. Now, it's pretty easy. What we have to do is set up our equation. So we have m, our slope, is equal to the change of our y's. So I have 3 minus a negative 2 over the change of our x's. So I have 8 minus 8. 3 minus negative 2 is like 3 plus 2, that's 5. 8 minus 8, 0. Whoa! Wait a minute. We can't divide by 0. Not at least till calculus 2. And then even then it's cheating. So what did we come up with? If we ever get a situation where you have a number divided by 0, this is undefined. Undefined. What we're actually looking at, if you were to look at these points graphed, just as an FYI, and some of you may have seen this already, is that at 8, 3, you have a point, and at 8, negative 2, you have a point. You're dealing with a vertical line. Huh. So let's talk about some slope rules really quick, shall we? Let's get some board space first. So slope has a couple different options, if you will, as you're looking at what it might appear. So I'm going to put my graphs up here just to give me some situations. We know 4 things about lines. Very, very important. Right off the bat, we already know them. We don't have to know anything special about them at the moment. We know lines can go up. We know lines can go down. We know lines can go flat. And we know lines can go vertical. Now, in these 4 situations, slope is defined for all of the situations except one. And we just encountered that situation. Slope is undefined for vertical lines. That's an abbreviation of undefined. So slope is undefined for vertical lines. Very, very interesting. Now, remember, a vertical line is of the format x equals a. So whenever you're looking at x equals a value, there's no other y variables or anything of that nature, x equals a, that is a vertical line and it has undefined slope. If you're looking at these situations, we read from left to right. So left to right, what we're looking at is this line is increasing. So slope here is positive. That's a little plus sign inside of a circle. Left to right here, slope is negative. Little minus sign inside of a circle. And here, slope is 0, or you may see slope has no change. I apologize, math teacher, not an English teacher. There we go. So math has no change in that last example there. So what are we actually talking about for our equations? I want you to see the similarities. That's why I'm introducing this idea now. There is an equation that we will learn in just a little bit, which talks about the slope-intercept form, meaning you can identify the slope within the equation itself. And that is of the format y equals mx plus b. So what we're saying is, in this equation, for this example, slope is positive because it's moving left to right going up. The same equation can be used here, but the difference is the slope is going down, so the graph is going down, and the slope is negative. That's the key difference. The equations are essentially the same kind of format, but the slope makes the difference of up or down. In this situation, you have slope as 0. Slope has no change, which means if you were to look at that same format, there we go, 0x plus b. If you were to look at that same format but plug in 0 for m, because m is 0 here, then what you get is y equals b, which is a horizontal line. And you've encountered a few of these in graphing already. Now, notice, again, these 3 on top have slope defined. This one has slope as undefined, and there's a very easy way to remember this. Mathematicians, when they were coming up with all of these really hard equations, decided they needed a vacation. And so where did they go for vacation? Math-YE. Yes, Math-YE. It is paradise island of math. That's what it is. Now, Math-YE, how do you get there? You get on a plane, you take off, you fly for a while, and then you land. Nowhere in that trip to Math-YE did you go through this kind of motion. If you did, you're not going to Math-YE. Just saying, this is a vertical line, you would be crashing. The other way you can think of this is these are like stairs going up or going down. This is the floor of the building that you're going to. It's flat, be glad of that. And these are the walls holding that building up so that you can actually go up or down. So there are different ways to think about this. I prefer Math-YE, but that's just me. All right, so that being said, let's dive deeper into slope-intercept form. I think now's a good time anyway, partly because it's also on your notes. So as we're looking at our slope-intercept form, we have y equals mx plus b. A couple key components. You have slope, and then you have the value of the y-intercept. I say value because a y-intercept is a point, it is a location. This is simply the value of what the b value would be in that point. So what does this actually have? It has variables, it has slope, and it has the y-intercept value. The slope and the y-intercept value are constant values. That's what those are. The only thing that changes are x or y, because those are variables. So if I'm looking at this particular problem, 3x plus 2y equals 6, it's currently in standard form for linear equations. Remember that ax plus by equals c? That's what this format looks like. We want to move to slope-intercept form. So we want to determine some information from this problem without actually having to go through tons of graphing and everything else, trying to count our points and all that stuff. So here's what we're going to do. Notice the slope-intercept form is solved for the variable y. We're going to do the same thing. We're going to solve for y. So subtract that 3x over. That's 2y is equal to a negative 3x plus 6. Notice how I wrote my x before my constant. That's okay. You can do that, just don't lose your signs. I'm going to then divide by 2. Y equals a negative 3 halves x plus 6 divided 2, 3. Awesome. What does it mean? Well, from here, now that we are in slope-intercept form, we know the slope is negative 3 halves. How does that help us? We know that this graph is going down. Because our slope is negative, our graph will go down. What does this 3 mean? Well, if we were to plug in 0 for x, negative 3 halves times 0 is 0, plus 3, y would equal 3. So this is the y-intercept value right there. This being your actual y-intercept. So what you have done without actually having to graph is determine the slope and the y-intercept. Pretty awesome. It comes straight from an equation. From here, if you were to graph, you would only need one more point. And so you could easily plug in a 2, since this has a denominator of 2, and solve that out to get a second point and then graph. Very easy, very straightforward. Now, I'm going to erase my notes here. If you didn't write those down, I highly suggest going back just a few seconds in the video, pausing, writing them down, because you're going to need them. Really helps give a visual. Let's try another one. Let's say I have 4x minus y equals negative 8. We want to write into slope-intercept form. So I'm going to write my equations here. This is slope. Y equals mx plus b is slope-intercept form. And so I have a standard form equation right now. I want a slope-intercept form equation. I solve for y. Couple ways you can do this. Y is currently negative, so I'm just going to add it to the other side. Adding that y over and adding this 8 over, I have y all on its own. And then I have 4x plus 8. There I go. You could technically flip this around so it looks more like that. You have y is 4x plus 8. It's the same exact thing. Question, what is your slope? And what is your y-intercept? Well, the slope is always attached to that x value, so slope is 4. Y-intercept is always 0, and then whatever this b value is, that's 8, so 0, 8. What about in the equation, y is equal to negative 4? What is your slope? 0, right? How do you know? How do you just look at that and know, right? Because that seems really strange that you could just, boom, that's 0. Yeah, that's the slope. Remember, in our situation with our notes, you had 4 types of slope graphs. That third one was when slope was a horizontal line, it had 0 change or no change. That meant your slope is 0. What is your y-intercept? 0, negative 4. How do you know? Well, let's rewrite this problem. Maybe it'll be a little easier to see. Y is equal to 0x minus 4. You're in that slope-intercept form. 0 times x is just 0. So you have the same format either way. It's just this is the simplified version. Excuse me. All right, let's try another one. Let's try, I got plenty of room right here. I'm going to put it right there. Let's 5x minus 2y equals negative 2y. Excuse me. Okay, so if I'm looking at this particular problem, again, solving for y, I'm going to divide that negative 2. I have negative 5 halves x is equal to y. This means my slope is a negative 5 halves. What is my y-intercept? 0 what? That may be a little bit of a challenge, right? Not really. Technically, this is y is equal to a negative 5 halves x plus 0. Your b value is 0. You cross through the origin. That's all that means. So as you're looking through different types of linear equations, in my personal opinion, as well as the opinion of many others, but I can only speak for me, the slope-intercept form is probably the most useful form for linear equations, and that's because it gives you the most amount of information with the least amount of work. So we're going to go ahead and erase these. Just get me some board space. And the next section is talking about parallel lines and perpendicular lines. Now, to have lines that are parallel, just to give you a visual, you have 2 lines that will never intersect. These 2 lines just keep going in the same direction. They never, ever intersect. These are parallel lines. Now, we typically use this symbol to represent parallel. And so you may see it as like a subscript, like M is parallel, or you may see that one line is parallel to another. But that's typically the kind of notation that we use to indicate parallel, just in case you happen to see that. The slope for each line is the same because they are changing in the same direction. They never intersect. So the slope for parallel lines is the same. Perpendicular lines are just the opposite. So you have one line going in one direction. You have another line that comes through and intersects this line at a perfect 90-degree angle. It has to be exactly 90 degrees, otherwise it's just an intersection. Perpendicular lines, we typically use the upside down T symbol to show that it is a perpendicular something. So in this case, it would be perpendicular slope, just to give you that indication. And your slope for these types of lines, if you have one given slope, the other slope is opposite and reciprocal. So the other slope is the opposite and reciprocal of the first. Now, let's work through a couple examples. If I have a slope that is given as 3, the question is, what is my parallel slope and what is my perpendicular slope? So if I have a given slope of 3, my parallel slope has to be the same. That's easy. My perpendicular slope has to meet 2 conditions. It has to be opposite and reciprocal. Right now I have a positive 3, so opposite means negative. And reciprocal of a whole number means you have 1 over that value, because this is like 3 over 1. The over 1 is implied here. To reciprocate that, that would be 1 over 3. And that would be your perpendicular slope. What if I have a given slope of negative 1/4? My parallel slope is the same. But my perpendicular slope is the opposite. So this is negative, it's going to be positive. And the reciprocal. So this is 1 over 4. Flip it, that's 4 over 1, which is just 4. Let's talk about our slope of 0. Remember, this is that flat horizontal line, slope of 0. A parallel line is going to have the same slope. That's pretty straightforward. But a perpendicular line, ooh, interesting. So if I have a slope of 0, technically there's no sign on 0, but since I don't see one, let's call it positive. Opposite would mean that we're looking at something negative, right? This is like 0 over 1. Kind of, if you thought of it as a whole value, it's technically an integer, but let's think of it as a whole value for a moment. 0 over 1. Reciprocal would be 1 over 0, but you can't divide by 0, which makes this undefined. And that makes perfect sense. If this is a horizontal line, then the perpendicular line has to be vertical. And so what we're seeing is quite literally, think of the axis, you have a horizontal line, and then you have a vertical line. And that is your perpendicular line, or perpendicular slope, undefined, for a given line with a slope of 0. Okay, so let's move on a little bit. Let's put this into practice. If I have 2 equations, such as the 2 that are listed on your notes, so I have y equals 3x minus 7, and then I have 3x plus y is equal to 4. If I have these 2 sets of equations, the question is, determine if the following are parallel, perpendicular, or neither. Now, how do we do that? Right now, I would say, looking at our 2 equations, I have one in slope-intercept form, so I can identify the slope really quickly. It's 3. My other equation is in standard form, so I need to simplify this into our slope-intercept. So I'm going to move that 3x over. That gives me y equals a negative 3x plus 4, which means my slope is negative 3. How do I determine whether or not these are parallel, perpendicular, or neither? Well, I have to compare the slopes. are the slopes the same? Like exactly the same? No, they're opposite in sign, which means these two lines are not parallel. Question, are they perpendicular? So I have a slope of 3, I have a slope of -3. They are opposite, but they are not reciprocals of each other. So these lines are not perpendicular either, which means the solution here is that these are neither perpendicular nor parallel. They just intersect at some point. That's it. Okay, guys, that is it for section 3.4. Really good, thorough introduction to slope. I will be continuing into the next section in another lecture.